Hello students, this is Dr. Ben, and we have an example problem out of the last part of Chapter 4 that has to do with the topic of projectile motion. So this problem involves baseball, and specifically it is a catcher throwing the ball to the second baseman. And it gives us a lot of information about the situation and asks us to find something about this throw. And so when we set up this problem, we need to be very careful about the geometry. And so one of the things that we notice is that the final position of the baseball is the same as the initial position. So even though that might not be on the ground, the baseball doesn't have any change in vertical position in the whole process. So that'll be important to recognize on our pictorial representation. And then the other thing we notice is that the ball is launched upward, so it goes in kind of an arc as it comes back down. So let's go ahead and draw this pictorial representation on an XY coordinate system. So let's pick the position of the catcher when the ball is thrown to be at the origin, and we'll just kind of trace out the motion, and we see where the second baseman needs to be at the same elevation. And then another point that will come in handy in this problem is the top point, and we know at that point we have the special condition that the y velocity is equal to 0. At that point it's a turning point. Alright, let's label our points 1, 2, and 3 and indicate the direction of the acceleration is caused by gravity. And I think that I'll omit putting all of the kinematic variables on this diagram because there's a lot of them, but we'll go ahead and put the ones that we need in our table of what we know and what we want to find. So probably it would be good to recognize what it is we want to find first of all, because we really didn't acknowledge that very specifically. We can see that's here in the last part. How much time does it take for the ball to travel the 120 feet? And so actually that's going to be the value of the quantity in the diagram that would be labeled as T3. So that's the time at which the ball is going to land. Alright, so we can go ahead and write down what we know. So the value of x1 is equal to 0. The value of x3 is going to be equal to the 120 feet that's given, and actually the value of x2 is 1/2 of x3, because for projectile motion in which the starting and the ending points are at the same elevation, then the motion is symmetric. The object travels the same distance up as it falls. The decrease in the velocity on the way up is mirrored by the increase in velocity on the way down, and so the motion diagram has a symmetry to it. As far as the time goes, we'll set T1 equal to 0. T3 is what we want to find, and again by symmetry T2 is going to equal 1/2 of T3, because it takes the same amount of time for the projectile to make it to the turning point as it does back down. And in this problem, a sub y is going to be equal to -g, and since the numbers are given in the English system, we remember that g is 32 feet per second squared. Alright, so we ultimately want to find the time that it takes for the catcher to catch the ball, and so that's going to be the value of T3 at the end of this. It's going to be quite hard to find that to begin with. It may be easier for us to find the value of T2, which is how long it takes for the ball to get to the top of the motion. That T2 may be in terms of the initial velocity v1, but we can at least find an expression for that, and then once we've got that value of T2, then we can double it to find the value of T3. All right, so that's what our strategy is. So we have to kind of divide and conquer and consider this problem in steps. So perhaps it would be best to start with the y direction. And if we go from point 1 to point 2, we know what the value of the velocity in the y direction is at point 2 because that's the turning point, and that can be very useful. So I would like to write down the kinematic equation for the velocities and the time and acceleration from point 1 to point 2. It seems silly to do anything with the vertical position because that just adds another variable. So let's say that v2y equals v1y plus ay times t2 minus t1. All right, on my diagram, I need to go back and add the initial velocity v1 and its angle that it makes with the horizontal x-axis so I can get the velocity components that I need. All right, so we can't do this completely numerically at this stage, but we can plug in some numbers because at point 2 the y velocity is equal to 0. So 0 will be equal to v1 times the sine of theta, because that gives us the y component of the original velocity, and then minus g times the quantity t2, because t1 is equal to 0. And if we solve this expression for t2, then we get v1 sine of theta divided by g. All right, so it would be nice if we could come up with a numerical value at this point for this time, and then plug and then double that to get t3 and get our answer. But as you notice, we can't do that at the moment because we don't know the value of v1. But we can find the value of v1, at least in terms of the x part of the motion, and see if we can combine things together to eliminate that. So let's move our paper up so we have a little bit of work. So I'm not exactly sure which way to go, but we only really have one equation in the x direction that can be helpful because there's no acceleration. So we might as well go all the way from point 1 to point 3 in the x direction. So that means that we would say that x3 was equal to x1 plus the velocity in the x direction times the quantity t3 minus t1. All right, so the value of x3 is a known quantity. The value of x1 is known to be 0. v1x would be equal to v1 times the cosine of theta, and then since t1 is equal to 0, this last term is t3. And so if I would simplify this expression a little bit, I would have that x3 is equal to v1 cosine of theta times t3. All right, so if I put those two equations together, I'm not going to be able to eliminate the velocity although maybe what I need to do is just to approach this as though I have two equations and two unknowns and try to eliminate the velocity. So maybe that's a better approach. So let me move my paper up a little bit so we've got some space to work. All right, so let's take the first equation and solve it for the velocity v1. So that would say that v1 equals t2 times g divided by the sine of theta. All right, if I take the second equation and solve it also for the velocity v1, I have v1 is equal to x3 divided by t3 times the cosine of theta. All right, and now what I need to do is to combine those two together. Since the left-hand sides are the same, the right-hand sides are the same, remembering that t3 is equal to 2 times t2, and now I only have one unknown, and I can actually solve for it. So let's take the left-hand side, t2g divided by the sine of theta, and then the second equation's right-hand side, x3 over t3 cosine of theta. Now I'll cross multiply, so I get t2 times t3 equals x3 sine of theta divided by cosine of theta multiplied by g. So the g comes downstairs, the sine goes upstairs. All right. So on the left-hand side, I'm going to write that t2 is equal to 1/2 of t3. So 1/2 of t3 multiplied by t3 is equal to the right-hand side, which is x3 times the sine over the cosine, which is the tangent of the angle, divided by g. So now if I multiply through by 2, I get t3 squared equals 2x3 tangent of theta divided by g. And there we go. All I need to do now is to take the square root of both sides. So t3 equals the square root of 2x3 tangent of theta divided by g. And now we have all the numbers that we need from the problem. So we have x3 was 120 feet. The angle was 30 degrees. And again, we remember that the acceleration due to gravity in the English system is 32 feet per second squared. So we'll get our calculator. 2 times 120 is 240, times the tangent of 30 gives us a 138, and then divided by 32 gives us 4.33, and I take the square root of that and I get 2.08 seconds. So I'm going to round that to 2.1 seconds, and that's going to be the value of t3. 2.1 seconds. So we've got our units, and we've got our significant figures, and we accomplished the problem, which took us a few steps. It took the catcher 2.1 seconds for the ball to get to the second baseman.